I'm Chris Elsworthy. I'm the lead engineer and CEO of a company called CEL UK. We're here in the Kickstarter hall to talk about our journey from basically university all the way up to where we are today as an international manufacturer of consumer products and UK developer of 3D printers. A little bit about our history and who we are. So we're based in Portishead, which is just outside Bristol in the UK. We're a team of 14 people, which includes 4 hardware engineers and 2 software engineers, and a lot of admin to keep our products in manufacture and logistically distributed around the world. All our products are based around innovation. We try not to compete on price alone, because that's a losing game. We try to work in areas where we can add innovation to new products, make them a little bit different, or solve problems on the market already. I started in floor care products with a guy called Nick Gray, and helped him develop his first product, which was the G-Tech floor sweeper, which is a cordless battery-powered cleaner. That battery technology took me to power tool manufacturers in the Far East, where I helped them develop power tools and garden equipment all around new battery technologies, including what is now the current standard lithium polymer and lithium-ion batteries. That journey took me to Dragon's Den, where I presented some of my power tools, and in particular the Power 8 workshop was featured on that presentation. And for those of you who haven't seen that product, it's a 4-piece cordless power tool set, which uses the case in combination with one of the handheld tools to become its benchtop equivalent. So, for example, the handheld saw becomes a table saw using the case. Through that, all the development of those products, we've heavy users of 3D printing, and we were buying in prototypes and playing with rep-wrap machines to develop the product, and we were modifying those to work as results-oriented machines. So rather than my engineers spending a lot of time tinkering and playing with 3D printers to make them produce something, we were trying to modify them so that you just press print and out comes the result. That led to the development of a product called Robox, which I'm going to talk about mostly in this presentation, and that was successfully funded on a Kickstarter campaign back in 2013. That has been successfully launched, and we've had subsequent products in the Robox Dual, and this month we've launched the Robox Pro. So to wrap it all up, CEL UK is a product development company, but we've got the feature and power to produce our own products in the Far East and in the UK, and take those products to market. Why did we choose to do 3D printers? This is because back in 2013, the hype bubble, as it was starting to peak. There's a lot of 3D printers on the market. We were using quite a number of them to develop our other products. But we found that there's a great rep-wrap community. If you don't know what that is, it's people that make printers using off-the-shelf components and share the designs openly. We found that there was limitations with that type of technology. You couldn't evolve the technology beyond some constraints, so we tried to take it to the next level, whereas we've designed a new level of software and hardware and firmware, which all work together to try to give you a single, more flow throughput of 3D printing. Unlike the power tool market, which we're already in, there's no real leading brand. There's an emerging market, so you have some players in the market already, and you'll probably heard them like MakerBot and Ultimaker and Stratasys and 3D systems. But compared to power tools, where you are either a Bosch buyer or a Makita buyer or a Black & Decker buyer, and you're a very loyal brand advocate, people still look for innovation in this market and don't just focus on the brand they want. So we thought it was an opportunity for us to develop a product where we could build and establish a brand, especially in the UK. Our experience of developing high-tech and innovative products is natural for 3D printing, because you can either go and download an open source product and make a 3D printer yourself today for a very low BOM of around £200, but you can also continually innovate on that design and share those designs on the internet. But we wanted a printer which you could take out of the box and you not be an engineer, not be technically able, and be able to start 3D printing your ideas. And that was also driven by a personal thing of mine of having two very dyslexic children, including myself, who like using computers as an interface portal, but want to get a three-dimensional result from that. Now, if any of you have got kids, you know how great at CADing things up they are. They're probably extremely quick users of things like Minecraft, which is probably the most basic CAD package in the world. But you can make incredible things if you've got the right imagination, and that's what children do. So from all those things, we started to look at what was currently available on the market. So this is the very first 3D printer I bought back in 2005. When I say bought, I bought a 3D printer. I paid for the parts to be printed on a Stratus machine, which is a £50,000 machine, and I made the parts from bits bought from Amazon and eBay. That is a design that is available still today through the RepRap community. We quickly realised that not everybody is a tech head like me, and although lots of people like to make things, not a lot of people would like to know how it's made. They want to see the process. 3D printing is a mesmerising process. It's been likened to watching fire. You can spend hours watching something appear from nothing. But how that happens is not really relevant to most of our market. They want to see the thing being created, but not have to worry about any of the technology behind it. So we developed a system which would expose on three faces the process of 3D printing, but hide away as much of the technology as possible. So the technology itself would be the focus of the design. A lot of products on the market in the tech space are very polished and finished. I mean, if you look at any phone or household appliance, which is where this market hype cycle was going, everybody was going to have a 3D printer around the 2013 point. We wanted the product to look consumer-based, so we want a very strong chassis. And this design incorporated one main member. The plate of steel at the bottom was the reference plane, and all mechanical parts in some way touch that component to reduce the amount of tolerance between the moving parts. Our design quickly moved to how to produce that in mass manufacturing. So you can't weld together big lumps of steel, fettle them by hand every time you want to make a printer. So we quickly moved to our experience with injection molding and pressed metal, but to try to keep the quality feel of the product that we had in the full metal product. So we started to use aluminium wraps and injection molded parts, but we still kept the stainless steel reference plane in the bottom of the product. Through a number of iterations, we used our own development products. So every time we made a 3D printer, we used it to print the next generation of 3D printers, so they were self-reproducing, until the point where we wanted to start cutting steel to make injection molding tools. At that point, we paid for a SLS prototype, which was green in this case, and that went towards making the first injection molding tools, and the design process was started there. As I said before, we successfully ran a Kickstarter campaign raising and selling £300,000 of capital. That has helped us pay for the development and the production of the tooling equipment to make the product. And that led to our first launched machine in 2013. Now, there's a lot of features that we put in our products which make it completely unique from other 3D printers on the market. And they include things like the repetitive stuff that we were finding ourselves doing over and over again. So bed leveling, for example, you have to make sure that your first layer of print goes down flat on the bed you're printing it on it. On our machine, we developed a way that the nozzle itself could probe the bed in as many points as you want. We use actually 9 at the moment. The firmware inside the machine writes a topography of what the bed surface looks like, and then prints the part using the topography of the bed and some clever maths equations. That topography can then be washed out over however many layers you want to then go back to a flat planar and repetitive two-dimensional process. And I don't know if I'm teaching you the psychics here, but 3D printing is basically a repetitive two-dimensional layer process. So you lay down a layer of plastic, you move up a little bit, and you lay down another layer of plastic. And by doing that, you can create any three-dimensional shape you like. Our product today on the market is multi-polished. We've also now moved to multi-materials. We can process multi-materials at the same time. But the important thing here is a lot of the design we put into the product early on was already future-proof. We made the project very modular. So, for example, the head can be removed and replaced, the extruders can be removed and replaced, the main board can be replaced. It's very serviceable and upgradable. One of the ethoses we have in designing products is that if you invest a lot of money in a piece of hardware that we sell you, we want that piece of hardware to stay with you for a very long time. So when we develop the next head, we don't want you to bin that product and buy the next generation. We want to offer parts to upgrade your machine and continue using that as you go through. So if I talk about some of the innovative features and what makes the Robox different, the first thing is, and lots of people tell us, is the build volume is relatively small. This is an intentional thing, and we might lose sales because of it, but it is very intentional and part of the design concept and true to what we're trying to make 3D printers do. Most 3D printers live in someone's garage or workshop or outside building, away from where you actually do the design work. So we try to make the build volume no bigger, and the whole machine itself no bigger than a domestic 2D printer. The idea being that if you're working in CAD and designing parts in a day-to-day basis, that you can throw small parts of your design philosophy or design intent at the machine, prototype that part while you're moving on a different part of the machine, and generate proof of concept models all along the process of development. If you have to leave your chair, go downstairs, go to the garage, go to the workshop, or wherever you keep your 3D printer, that chain between development and prototyping is a little bit lost. So we try to keep the machine small and compact, and in fact that has enabled to penetrate a number of markets. One of them being education. We didn't know at the beginning, but most schools don't like to leave hardware running overnight. So they need machines which can produce parts in under 8 hours the working day. So rather than having one very expensive large machine, they much prefer the idea of having multiple smaller machines so they can produce parts for all 30 children in a class within that hour or within the school day. So the size of the machine was very important, and keeping aspects like the power supply and the consumable parts, in this case the plastic reel of filament, inside the build volume were very important to keep that kind of desk-based machine. The product is fully assembled out of the box, so you can literally take out the box, plug it into your USB drive and start printing within a matter of minutes. The head, as I mentioned before, is easily replaceable. So as we develop new technologies, in this case this is the dual material version, which is exactly the same as the single material version, but there's an extra extruder added and the head has been replaced. Self-calibrating, so if you don't want to program what type of material you're using or what type of head there is, you can simply select the part you want to print, press its quality, which is basically in this time the time you've got available, either high, medium or low quality, and make it go. Automatic reel recognition, so whatever material, we produce something like 25 different types of polymer now that this machine can process. All those use different parameters for 3D printing, whether it be temperature, the environment, the temperature of the environment they're being printed in, the heat of the surface they're being printed on. That's all automatically programmed by data which is on the reel of filament itself. And again, some of the flexibility. One of the parts that 3D printers have tried to solve for a long time is what to print onto. In some cases this is hairspray or masking tape. There's 1,000 different types of solution over there. We actually developed and brought to market the first polyether imide bed, which is an aerospace material which is extremely thermally stable. So that means when it heats up, it doesn't change shape or size. Most of the polymers, although we print with, do change shape or size when they're printed. So you heat up the bed, you lay down your hot plastic on top of the bed, and then when you finish printing your part, you allow the chamber to cool down. The bed itself doesn't change size, but the part shrinks a little bit. In that case, it just snaps off of the bed and with a clean, and you can lift it off. most 3D printers you need a scraping tool or some such device to get the part off of the machine after it's printed. And one of the very important features we didn't think would be particularly relevant to the market was the fact that the lid locks and closes. Now, apart from the obvious not being able to stick your fingers in and touch the really hot bits, this enables us to control the environment that the printing process is happening in. Therefore, we can print with a much wider variety of materials. I talked a little bit about future-proofing our hardware. We know that technology is continually developing. We know that 3D printing in particular is developing extremely rapidly. So we wanted to make sure that our product was sold with in mind that you can upgrade it at any time. And this comes with features like this. So the head itself can be easily replaced with one thumb wheel. It has a CAN bus which controls all the data to and from the head, so that you can replace that with any head. And at the moment, in development, we've obviously finished the dual material head. We're developing a paste extrusion head which can print, which will be able to print ceramics or silicons or conductive inks. We've also developed a stylus cutter, so it turns a 3D printer into a plotting machine or a vinyl cutter. It can do lightweight CNC machine. It can also do pick and place for electrical component placement. Again, going back to that philosophy, once you've got this Cartesian action, this XYZ movement on your desktop, the end effector can be changed to do whatever you want, and thus the name. It's a Robox in a box. Currently on the market, we've got 3 different types of head. The original one is called Quick Fill, and the reason for that is because we have a single melt chamber, which means you can feed a single material into a hot block of metal, and it can exit from one of 2 different sized nozzles. If you liken this to having a very thick marker pen and a fine marker pen when you're doing a technical drawing, you can very quickly draw a detailed line around the outside of your 3D printed part, and then you can quickly hash in the centre with a thick nozzle. It also gives the machine a very wide variety of resolutions that it can print in. The technology we developed to make this is completely unique in the market. We can actually shut the flow of material off right behind the needle, enabling the machine to pick up the nozzle that it's not using and put down the nozzle you are using and close off the flow of material from whichever material you want. That enabled us to develop the dual material print head very quickly, which has 2 separate melt chambers and it can process 2 completely dissimilar materials at the same time. And the obvious one is obviously multicoloured parts, so you can print multicoloured parts, but you can also print 2 dissimilar materials. So you might want a structural material and a flexible material, or you might want a rigid material and a water-soluble material that you can use for support and printing difficult to construct shapes. The most recent head that we developed is one that allows our users to experiment with 3D printing. It uses a standard M6 nut on the nozzle, which means that you can put on any type of nozzle you like, but the one it comes with has a ruby embedded in the tip, which is an extremely abrasive resistant material, which means you can process very strong mechanical parts, including glass-filled and carbon-filled parts. Very recently, we've just launched our latest product, the Robox Pro, and this is in answer to our own customer base. Although our philosophy was to make a very small machine and keep that on people's desks, because of the amount of technology that we developed for Robox, people wanted a bigger version of it. They wanted to produce bigger parts. So we tell them, buy 2 machines, print it in 2 pieces and glue them together afterwards, because that way, like a RAID array for computers, you get more security. If one part fails, you haven't lost the whole print. You can print faster because there's multiple nozzles working on the same job at one time. But people don't listen. They want a big machine, so we produced a big machine. And that includes all the development we've made on 3D printers along the way. So that includes the network functionality we made in Roots and Moat, which is a 5-inch touchscreen, which has a Raspberry Pi behind it, controlling all the network functionality. You can do, because it's a mini PC, you can do a lot of the functionality on the front of the machine, so you can do all the maintenance, cleaning, changing materials, automatically, rather than having to plug in your PC using a USB port. And it also enables it to be connected to your local LAN and wide area network to share amongst your peers. So that printer is now manufactured in the UK, where our original Robox 3D printer was manufactured in China. So why have we moved away from mass manufacturing? Well, for several reasons. The first one is the hype cycle of 3D printing never really materialised. Everybody thought that 3D printing was going to be in everybody's home, like the Star Trek Enterprise, by the end of the week, and we're all going to be printing our own replacement ears and kidneys on our own 3D printers. The technology just isn't that great yet, unfortunately. We're striving towards that, but it's not there yet. We can produce awesome 3D printed parts, which are brilliant to use in everyday applications, but not kidneys and ears yet. Although I'm sure there's people working on that. Also, by volume, our last 3D printer, the Robox, is still the largest market in the world. Those machines are sold in huge numbers around the world. But by value, the largest market by far is the prosumer, people like yourselves and all the guys out there working in industry, and higher than that, the industrial users who use 3D printing for producing parts on an industrial level. So we are now developing markets, printers obviously to fit that market. We want to be growing at those speeds. So that coincided with Brexit, good or bad. That devalued the Great British pounds, which made our spend in US dollars into China much less. So the value of our products become much more expensive, and thus our profit margin dropped. So by manufacturing in the UK now, we can retain some of that profit. And also, although the machines are more valuable and higher in price, we can produce them in low volumes. And the really important part about this bit of the story is that we have tightened our development cycle. We physically produce the machines in the same office as we design them. So every machine, or every batch of machines that we produce, is a little bit different to the last batch, because every day we make small tweaks and improvements to our design. And if you go and pay for £1 million worth of injection molding tool to make your 3D printer, and then every week you want to change it, your manufacturer's going to get pretty pissed off with you, because they're never going to be able to produce the parts in volume. But the way we're producing parts now on 3D printers and CNC cutting machines, we can make every design a little bit better than the last one and continue with the market pace, making our machines relevant all the time. We have all completely organically grown to this point, so all our income has been from selling and making 3D printers. This year we've managed to secure 2 Innovate UK grants, which are going to help us fund the next stage of development of 3D printing. And as I kind of briefly touched on before, 3D printing is a repetitive two-dimensional layers. We know that we can change that and improve 3D printing. We're also starting our very first funding round, and we're out there looking for investment, and our 2 Innovate UK grants are helping us do that, because the technologies that we're developing are extremely disruptive in a number of high-value markets. So what is that? What are we doing? What's new? So our 3D printers can print with a huge range of polymers at the moment, but there are some very expensive, very unique industrial polymers, which our next Robox Pro and our next machines will be able to print in, and they're Alt-MP PPSU. These materials are very high temperature and can be used in real life situations like F1 cars, etc., and aerospace industry. Our first Innovate UK project we call Impact, and I forget what the acronym is now, but it's really cool, but I've forgotten it. And what we're going to be doing is we're going to be taking what is a repetitive two-dimensional layer process now and making that into the 5-axis CNC machine equivalent. You say, why do we want to do that? Because that's just making it more complicated. Because it adds a number of huge benefits. It moves 3D printing from what is a prototyping technique now, or a low volume manufacturing process, towards and next to more traditional manufacturing processes like injection molding. And as an example, you can imagine an injection molded part can be taken off of an injection molded tool, placed inside our impact machine, and we can add conductive tracks. We can add features to that machine which the injection molding machine cannot add, undercuts, etc. And we can also subtractive manufacturing, so it can be part of the new Industry 4.0 technology which is coming along and add and be closer to traditional manufacturing techniques. Because you have 5 axes of movement, you don't have to start. If you imagine 3D printing starting with a flat tool, now you don't have to start with a flat planer anymore. You can start either with an organic shape and follow the surface of that shape, putting down your paste or parts. Or what we think is you can also add conductive tracks to those parts. So rather than having separate wiring looms in your product development, you can actually include those wiring looms into the structure and the mechanical parts. Now this has got a number of markets very, very excited at the moment. And the ones we're talking about, or talking to, for investment, and you can probably imagine the applications for these, is the automotive and aerospace industries. They're constantly striving to reduce weight in their products to make their products more efficient. But as technology goes on, more and more wires and connections are made and put into those systems. So if we can reduce the weight of that wiring loom by making structural wiring looms, the first thing is it can be automatically assembled. All wiring looms are hand manufactured at the moment and hand assembled into planes or cars. That can be robotically done now because you have a structured part where you know where all the terminators are. A wiring loom is also hugely over-engineered because it has to be handled by a human. It gets pushed into a box, shipped out from Thailand or wherever it's manufactured, and then unfoiled and put in through holes, etc., into the product that's being attached to it, whether it's a car or a plane. Those wires are normally 2 or 3 times over the gauge of the actual signal or power they need to transmit because of that manual manipulation. If you make that whole wiring loom structural, then you can remove a lot of the copper and the aluminium which goes to make the conductive tracks. This 3D printer can also not only add conductive tracks in the sense of transmitting electricity, but you can also lay down wire or other materials like carbon or Kevlar tows to strengthen a part in a 6-axis manner, rather than having repetitive 2-dimensional layers. So we're very excited about what's happening in CEL at the moment. Our growth has been organic till now, and we're going to be growing much, much quicker moving forward. And we're also excited about manufacturing in the UK. This is all new for me, and I'm very excited about doing it. So you can come and see our current machines up on the stand 79 upstairs, or come and ask me questions about them after this presentation.